In the appendix section 4, we are discovering if a sequence is monotonic. So we are considering the monotonicity of a sequence. So the word monotonic describes if a sequence is always non-increasing or non-decreasing. And this is not the same as strictly increasing or strictly decreasing. So, for example, a sequence that is non-increasing could be a sequence that is decreasing. But another non-increasing sequence could be a sequence that is sometimes constant or sometimes the same, but then otherwise decreasing. So I could say that this is a non-increasing sequence, whereas it is not strictly decreasing because we had two numbers in the row that were the same, whereas this the first sequence rather that I drew is not only non-increasing, but it looks like it is strictly decreasing. So when our sequence is either strictly decreasing or strictly increasing, that's when we would say that it is strictly monotonic. And in addition to that, a sequence can be monotonic past a certain point if it is eventually increasing or decreasing for all remaining terms. So for example, we could have a sequence where in the beginning something interesting happens, but then after a certain point that sequence is always decreasing. We might say that that sequence is monotonic from that point forward. So this would be monotonic and decreasing. So we will typically be interested in showing that a sequence is decreasing monotonically. And to show or to prove monotonicity, we could either use what we know about derivatives. So for example, if the derivative of a sub n, which represents again our explicit function of our sequence, if that's negative, then our sequence is decreasing. Or we could create an inequality that shows a sub n plus 1 is less than a sub n. So I could think of this as like my next term. Oops, those two words started to go together. My next term is less than the term that came before it, or my previous term. So if I think about it that way, if my next term is less than what came before it, and that keeps happening, that sequence is going to be strictly decreasing. All right, so in this first example, we are showing that the sequence a sub n equals 1 over n is monotonically decreasing. And again, we could do that two ways. So let's try it first using the derivative. So if I were to use this by taking the derivative of a sub n, I'm going to think of this as n to the negative 1 power. Oops. My derivative is negative 1 over n squared. And again, a lot of ways I could do this, but I could find my critical values of my derivative. So my numerator is 1 or negative 1, depending where you put that negative. My numerator can never be 0, so my derivative is never 0. But I know if my denominator of my derivative equals 0, that's a place where my derivative is undefined. So if n squared equals 0, that would happen where n equals 0. So I could test this on a number line. And really, I could think about values that are less than 0 to see what's happening to our sequence there. But remember, when we're working with a sequence, a sequence is a discrete function, and its domain is going to be the set of natural numbers. So what I mean is that we're never going to plug in a number that is less than 1 for n. Because when I number like terms in a sequence, I start with my first term. So all of that to say, we don't really care what is happening to the left of 0 on our number line. In fact, we don't even really care what's happening between 0 and 1, because I would never have like a term 0. Sometimes in Algebra 1 we talk about term 0, but a sequence truly does not have a 0 term. We start with our first term. So if I look to the right of the 1 on my number line, if I plug in any number, so let's say maybe the number 2, if I plug that into my derivative, I get negative 1 over 2 squared, which is negative 1/4, and that number is negative. So I know that my derivative of my sequence is always negative over here, which means my sequence is always decreasing. So we know that a sub n is decreasing for all n is greater than or equal to 1. So again, we could prove that using the derivative. Another way that we could prove this gets into something we might often do in a discrete math class in college, where we might be writing different proofs. We could prove that a sub n plus 1 is less than a sub n. And we could do this in a pretty straightforward way. So if I look at my explicit function a sub n plus 1 is just 1 over n plus 1, and we need to show that that is less than 1 over n. So our goal is to show that this statement is true. And we could really do that in two statements. One, we could show that n plus 1 is greater than n. Like, this is going to be true for all values of n. So n plus 1 is greater than n. Adding 1 to anything, any number, makes it greater than not adding 1 to it. So the next thing that we could show is that the reciprocal, so 1 over n plus 1, has to be less than 1 over n. So anytime I'm working with an inequality, if I find the reciprocal of both sides, that's another instance where I have to flip my inequality symbol so that my inequality remains true. So like, for example, I know 10 is greater than, let's say 2, but if I wrote the reciprocals of those numbers, 1/10 is less than 1/2. So anytime we reciprocate both sides of an inequality, we also flip the sign, almost like we're multiplying or dividing by a negative. All right, so we really were able to do this kind of simple proof in 2 steps. To show n plus 1 is greater than n, therefore those reciprocals, 1 over n plus 1 is less than 1 over n. All right, to take a look at our second example, we're showing that the sequence a sub n, which is 1 over n times the natural log of n, is monotonically decreasing. So again, we are trying to show that this is non-increasing. So let's try this by taking the derivative. So we're going to take the derivative with respect to n of 1 over n times the natural log of n. Due to there being so many letter n's, I'm going to put my argument of the natural log in parentheses. And I could do this using the quotient rule. This might be easier to do just using the chain rule, to think of this as n times the natural log of n to the -1 power. So, still haven't taken the derivative yet. So when we take the derivative using the chain rule, I get a -1 out front, n times the natural log of n to the -2 power, and then the chain rule tells me that I have to multiply by the derivative of the junk on the inside, which is 1 times the natural log of n, plus n times the derivative of the natural log of n, which is 1 over n. So we end up getting, for our derivative, the natural log of n plus 1 over n times the natural log of n squared and that is negative. So I'm going to put a negative out front. All right, so that's our derivative of the explicit equation for that sequence. So again, just like before, I want to look for anywhere I would have critical values. So if I'm looking for where my derivative is 0, I would look for where the natural log of n plus 1 is equal to 0. And that's going to happen anywhere the natural log of n is equal to -1. And I know to solve this equation, I need to exponentiate both sides with a base of e. So I get that n equals 1 over e. So that's going to be one of my critical values. I also have to consider anything that makes my denominator equal to 0. So if I'm looking at the denominator, that's where n times the natural log of n, that quantity squared is 0. We know we could take the square root of both sides, so n times the natural log of n equals 0. And then using the zero product property, this is going to be anywhere n equals 0 or anywhere the natural log of n equals 0. And again, if we exponentiate both sides, we know that is where n is equal to 1, or we just remember that fact. So if we go to our number line, we've got 3 numbers on our number line. We have 0, we have 1 over e, and remember e is about 2.7 and some change. So that number is between 0 and 1. And then we have the number 1. And remember, we are not actually going to ever plug in an n value that's less than 1. So of all these numbers, the only critical value that really matters is the 1, because we're working with sequences. So I don't have a term before my first term. So when I consider the sign of my derivative, I could plug any number that is greater than 1 into my derivative to see the sign. And so I could plug like a 2 or a 3, but I don't want to think about the natural log of 2 or the natural log of 3. That gets confusing. So what if I plug in just e? E is a number that's greater than 1. So I get, remember, there's a negative out front of my derivative, the natural log of e plus 1 in my numerator over e times the natural log of e, that quantity squared. Well, the natural log of e plus 1 is just 1 plus 1, which is 2. And my denominator is e times ln of e squared, which is just e times 1 squared, so e squared. So we get -2 over e squared. And since 2 and e squared are both positive, that negative out front makes our entire derivative negative. So we know our sequence a sub n is strictly decreasing from 1 on. All right, finally, in the last example, we are showing that our sequence a sub n is eventually decreasing. So this means that our sequence might not be decreasing for, who knows, maybe the first several terms, but at some point the sequence is decreasing. So again, let's try this one using the derivative. So if I take my derivative of a sub n, I'm taking my derivative of n over e to the 1/5 n, or n over 5. I'm going to use the quotient rule. So low d high, I get e to the n over 5 times 1, the derivative of the numerator, minus high d low. So that's minus n times e to the n over 5 times 1 over 5 from the chain rule. And then all of that over my denominator squared, or low. So when we get our derivative, we could factor out a common factor of e to the n over 5 in our numerator, which leaves us with 1 minus 1/5 n. And then in my denominator, I have 2 factors of e to the n over 5. So I can go ahead and cancel 1 factor from the top and bottom. And then the last thing we might want to do here, just to make this look a little nicer, is what if I distribute a 5? So like, what if I multiply the top and the bottom by 5, when I do that on top, I have to distribute the multiplication of 5. So our derivative is 5 minus n over 5e to the n over 5. All right, and again, we want to look for critical values. So we want to look for where our numerator or denominator is 0. So if 5 minus n is 0, this happens when n is equal to 5. So that's the input that will make our derivative 0. And for our denominator, I know 5e to the n over 5 is never going to be equal to 0 because that's an exponential expression and e to some power is never going to be 0. So I only have this one critical value of n equals 5. So again, if I look at my sequence here, if I were to plug in a value between 1 and 5, so let's say that we plugged in a value of 4 here. I'm going to get for my derivative 5 minus 4 over 5e to the 4/5, which is a positive 1 over a positive number. So my derivative of a sub n here, of that explicit equation, is positive, meaning a sub n here is increasing. So I use the test point 4. But on the other side of the 5, so from 5 to infinity, but I'm going to pick the number 6. If I plug in a value there, so let's say 5 minus 6, and again, we're plugging this into our derivative of our explicit formula, well, I get a -1 or a negative number on top over a positive number because our denominator is always going to be positive. So a negative divided by a positive is a negative. So we could conclude that our sequence a sub n is decreasing after the 5th term, so after n equals 5.